I have been working in this department for last 35 years. I have established I am Professor M.F. Wani, Professor Mechanical Engineering Department and in charge of High Temperature Tribology Laboratory. I have been working in this department for last 35 years. I have established one of the best laboratories in tribology in India, and we have developed the laboratory wherein we are able to develop the materials of our own, metallic materials and coatings, and then we test these materials in our laboratory. We conduct all tribological tests in our laboratory, and this laboratory is also known in the scientific world as High Temperature Tribology Laboratory. We have produced 13 PhDs in this laboratory and more than 100 MTech theses in this tribology laboratory. We have installed state-of-art equipment in the laboratory of tribology, and this tribology laboratory is also among 5 laboratories in India. This laboratory has already done MOUs with some advanced universities of the world, including Texas University and with other universities. We have got international and national collaboration in the field of materials. Tribological tests which we are conducting in our laboratory are unique in India, and this is the only laboratory in India which has low temperature as well as high temperature facilities. We have got the FIS scheme which we implemented, and we have already done research projects at international level with most advanced universities in the field of materials.
My name is Dr. Sheikh Shahid Salim. I am an associate professor in the Department of Mechanical Engineering. I joined this institution in 1993 and completed my master's from IIT Roorkee in machine design in 2002. I completed my PhD in the field of tribology in 2018 under the supervision of Professor M.F. Wani. My research interests include high temperature wear testing, friction materials and biomaterials. I have completed and supervised 22 MTech theses in the field of tribology. At the institutional level, I currently am the chairman of the Central Research Facility Center, which houses some of the most sophisticated equipment like XRD, FESEM, sputter coating, Raman spectroscope, etc.
I am Dr. M.S. Charu. I am presently Associate Professor at the Mechanical Engineering Department, National Institute of Technology, Srinagar. I worked on nanostructured lubricants and got my PhD in 2016 from National Institute of Technology, Srinagar. My research area is tribology, wear, nanomaterials, friction, and I successfully guided one PhD scholar in 2021.
I am Mohammed Hanif. I am Associate Professor in the Department of Mechanical Engineering. I did my PhD work on running in VR modeling. I have currently 6 PhD scholars registered on me. They are working on frictional noise, biolubricants, and both on experimental and modeling. I completed one DST project on high temperature tribological characteristics on non-oxide ceramics as co-PI, which has been submitted. Now I have applied for one DST project on biolubricants, wherein I am interested in investigating the lubrication characteristics of bio-oils, particularly jet oil. I have also worked a little bit about on neurosurgery modeling, which has been published. I have worked with some professors of SKIMS Medical Institute, the work has also been published.
Myself, Mohammad Mursleen, working as Assistant Professor in the Department of Mechanical Engineering, NIT Srinagar. I joined this institute in the year 1998. I did my bachelor's from REC Srinagar in the year 1996, master's in Mechanical System Design in the year 2007, and my PhD in the year 2018 with the title Debonding Analysis of Smart Beams under Mechanical and Thermal Loadings. My research interests are modeling and simulation of mechanical systems.
I am Dr. Mukundat Sharma, Assistant Professor in Mechanical Engineering Department. I have joined this institute on 1st November 2018. I did my BE in Mechanical Engineering from Bhopal, MTech and PhD from NIT Hamirpur. My research area of interest is materials tribology, optimization and modeling, nano coatings, design and manufacturing.
I am G.A. Harman. I am Professor HEG in the Department of Mechanical Engineering at NIT Srinagar. I did my Bachelor of Engineering from erstwhile REC Srinagar, that is NIT Srinagar, and my MTech from IIT Delhi, securing first position, and I did an integrated master's leading to PhD from University of Victoria, Canada. I have been associated with the Department of Mechanical Engineering for almost 41 years, out of which 36 years have been in teaching. I joined as an assistant professor in 1986, and then currently I am HEG professor in this department. My research areas are thin film lubrication, in which I have indigenously developed a test rig with the help of Ducom company. Another area is finite element method, and various other techniques like XFEM enrichment techniques have been utilized in computational mechanics, and 2 students are currently in this area of investigation, while 1 student has obtained doctoral degree in this program. Another area is erosion and erosive wear studies on turbines, that is hydraulic turbines, located in the region of Jammu and Kashmir, in which 2 students have done their doctoral program. They have taken the degrees, PhD degrees. In addition to this, there are students who are working in the area of fatigue and fracture mechanics, and all of them are in the final stages of their doctoral program. 7 students have already obtained doctoral degrees under my supervision. 8 students are currently under the scheme of doctoral program. In addition to this, 68 students have taken master's degree under my direct supervision.
I am Dept Prakash Sharma. I joined NIT Srinagar in 2016. My area of research deals with failure analysis, especially with fracture mechanics approach. My research is in the area of reliability of microelectronic packages.
Myself, Mohammad Marufani. I am professor in Mechanical Engineering Department. I have been in this institute since 1986. I have done MTech in Energy Studies from Indian Institute of Technology, New Delhi. I have done my PhD also from the same center of IIT New Delhi. I have done my postdoctoral research in pollution control from the Queen's University of Belfast, UK. I have done research investigations in the field of soot emission control in UK. Here also I am involved in academic and research in the field of internal combustion engines with my students and research scholars. I contributed in this institute by developing a new IC engines IC engines lab for undergraduate and postgraduate students. I have been doing research with AVL Austria on behalf of NIT Srinagar. I was principal investigator for this research project.
My name is Babar Ahmed. I am a professor in the Mechanical Engineering Department of this institute. I joined the department in the year 1992 as a lecturer, as was the case at the time. I did my PhD from IISc Bangalore in the area of micro-electromechanical systems. My work essentially involved the development of a capacitive micro-machined ultrasonic transducers, which would serve as an alternative to conventional piezoelectric ultrasonic transducers. We were actually looking to replace the piezo transducers in applications where contact with the surface was essential. We thought of a capacitive micro-machined ultrasonic transducer, which is essentially based on silicon micro-machining, and we were able to successfully fabricate and characterize the device. But currently my research interests are in the areas of haptics and control. So right now we are basically working on dual rate haptics controllers, and we're essentially trying to analyze the stability limits of such controllers. I also work on nonlinear systems to some extent. So we, for example, an inverted pendulum, a double inverted pendulum are actually areas of my interest. So I am in charge of the mechatronics as well as the dynamics lab of this department. In the mechatronics lab, we do work on projects which basically involve haptics and control.
My name is Saad Parvez, and I'm an associate professor in the Mechanical Engineering Department belonging to the stream of Industrial Engineering. Well, I'm presently heading a center which we established in the year 2016. We call it as an Innovation, Incubation and Entrepreneurship Development Center. Through this center, we are connecting the various departments of the institute to promote innovative ideas, helping the innovators of not only of this institute but the whole region. My research area is in the area of industrial engineering, value engineering, optimization, quality control and project management. This is the industrial engineering lab. So before the student actually starts his work in industries, so he need to know what exactly he need to do in the industries. So this lab helps him to simulate the activities vis-a-vis quality control is concerned, vis-a-vis facility layout and location is concerned, vis-a-vis material management is concerned. So all such activities we basically try to help him to simulate. We have different softwares which we are installed in the computers. One software is the Witness and the second is the SPSS. Both the softwares are basically simulation software where students are exposed to the industrial working in a simulation atmosphere.
I'm Adnan Qayyum, Professor Mechanical Engineering Department. I joined Mechanical Engineering Department in December 93. My field of specialization is experimental fluid mechanics and thermal engineering. I've done my master's from IIT Roorkee, my PhD from IIT Kanpur.
हेलो करना है हाँ आगे आगे हाँ आगे हाँ चलिए अस्सलाम वालेकुम चलिए लेट स्टार्ट वेलकम टू दिस एफडीपी आवाज वेलकम टू दिस एफडीपी आई एम अदनान कयूम one of the coordinators of this FDP. I'm also professor and head mechanical engineering department. So this FDP is organized by Department of Mechanical Engineering. So our mechanical department was established in way back in 1968. So in the early days, we were only having UG programs. So with the passage of time, we have added several MTech programs. Now we are having MTech programs in mechanical system design, MTech in thermal engineering, MTech in tribology and maintenance. Our department is having well qualified, experienced faculty. We are having state of art lab facilities and we can do very good experiments. At present, we are having an intake strength of 480 students, BTech students. 70 students have registered for MTech program, various MTech programs in our department, and 70 students have registered for PhD programs. So let's come to this FDP. So the title of this FDP is Thermal Characterization and Advanced Instrumentation Technique. So this FDP will run for 2 weeks. So we'll be having 14 sessions in this FDP. So in the first week, we'll be having 6 online sessions, followed by 8 offline sessions in the second week. So today we are starting our online session from March 13. So the timing of the session is from 7 to 7:50, followed by 10 minutes break. After that, we will be again resuming from 8 to 8:50, 10 minutes break, and we'll be having an interaction. So today our expert is Professor Andali Tariq. Professor Tariq is head professor and head mechanical and industrial engineering department at Indian Institute of Technology, Roorkee. Professor Tariq has done his MTech and PhD from IIT Kanpur. He has worked for several years abroad also. He is pioneer in the field of liquid crystal thermography in India. He has done extensive research in liquid crystal thermography for heat transfer measurements. His other fields of interest are optical diagnostic techniques for flow measurement, experimental fluid mechanics, cryogenics, and thermal contact conductance. And we are lucky enough to have him today. In fact, Professor Tariq has given consent for giving another talk on thermal contact conductance in the next week. So we'll be shortly starting our session today. So today's talk is the title of the talk is Digital Imaging and Liquid Crystal Thermography, Principles and Applications. So Professor Andalip Tariq will give a talk on this thing. So over to Professor Tariq. Professor Tariq, please start. हाँ प्रोफेसर तारिक वो आपका म्यूट है प्लीज वो अनम्यूट योर दिस थिंग हाँ म्यूट है we are not able to hear you your voice is muted your voice is muted you have a tab नीचे है ना वहाँ पे
Please click on the red button, red mic button. Please click on the red
Please click on the red mic button.
red
So, dear participants, please have patience. We are having some audio issue with our expert. He'll be joining shortly. अभी तो आवाज अच्छे से आ रहा था.
आ गया.
Coming now. Please speak. Huh. It's working now. So Professor Tagik will give a lecture on digital imaging and liquid crystal thermography. He'll be discussing principles and applications.
Are you able to see the screen?
Yeah. Everything is visible.
Are you able to see the screen?
Yeah. Everything is visible. Only you have to share this presentation. You are visible, but you are this. हाँ हेलो.
स्क्रीन आ रही है?
वो प्रेजेंटेशन नहीं आ रही है ना आपकी. प्रेजेंटेशन नहीं आ गई आपकी. You have to just वो.
अच्छा. अब आ रही है?
ना. अब आ गई. अब you have started. हाँ अब आ गई.
थोड़ा लैग है इसका.
चलिए ठीक है.
आ रही है अभी?
हाँ yes.
Can you hear me?
हाँ yes we can hear you. ठीक है.
हाँ. जस्ट एक वीडियो इस पे है अभी. थोड़ी देर में करो. हाँ मैं. हाँ थोड़ा. हाँ मेरी आवाज आ रही है या नहीं?
मेरी आ रही है.
आ रही है? ठीक है तो मैं स्टार्ट कर दूं?
यस सर.
Good evening to everyone. This is the name of my lab, basically ATAL, that we deals with the aerodynamic visualization and thermal analysis research lab, basically. And I'm the consultant of the BAR, CAPS, GTRE, and many more, TBRL, and many more agencies. So my research interest deals with the optical techniques, and that is the flow visualization, heat transfer enhancement, turbulence and flow control, solar energy utilization, thermal contact conductance, gas turbine blade cooling, and nuclear safety research. And our acquaintance is liquid crystal thermography, IR thermography, particle image velocimetry, flow visualization, and obviously some of the conventional tool that was used in the past, that is hot wire anemometry, cold wire, and thermocouples. Basically, our research philosophy is in the detail investigation. I always says that there is a proverb that God is in detail. Only the detailed investigation can give the real picture. We can see this diagram here. This is a flow around the sphere. In the left hand side, we can see that it is a 2D image. It depicts some of the vortex formation. And later, when we see the same thing in the three-dimensional volumetric PIV measurement, then the complete information get changed. So that indicate that the key of the understanding fundamentals lies that there should be a detailed investigation. And in that series, the present topic of the talk has been selected. The idea here is that to inspire and educate the scholars as well as the faculties, those who wish to do the research in the field of temperature mapping by using thermal liquid crystal thermography. So on that note, this we can say that this is a forward step, and it has a strong strength, and it has a strong implication in varieties of the application area. Now what I have done it, I have segregated my talk in two of the different units. The first deals with the fundamental, because right now we are going to deal the liquid crystal thermography, that is purely optical based imaging technique that gives the complete temperature patterns. So it needs the digital imaging. And obviously one has to understand the basic fundamental before diving deep into the liquid crystal field or any of the imaging field, where the idea is to map the temperature pattern by using the digital images. So one should have the know-how about how the digital imagings and what are the associated terms, how we deal it, what are the conventions, something of that sort. So in that way, this is the thing. So first we start working with what is basic of imaging. As we know from our school days that when we have to make the image basically, so image is getting inverted, and this is the typical discrete image. That become the basis of the image formation. And here in the discrete real value images, I mean, the analogous film based images, it is a continuous color at different discrete location. When we try to see that how the image are forming, so it can be categorized further in two of the different parts. The first deals with the geometry of the image formation, as we have seen in the earlier image that the pyramid get inverted basically. So that is dealing with the geometry, spatial wise, how it is looking into the image. And the other thing is that is the physics of the light. That is the which determines that the what kind of brightness, what kind of lighting, because again light is again a generic term. It varies between different wavelengths. So suppose we wish to understand what is light, so we are generally most of the time concerned with that we know that there exists the electromagnetic spectrum, and between certain range, say 400 to 700 nanometer, that is typically our visible range. That start working with the ultraviolet range to the IR range. We may have seen the Vibgyor pattern completely. So basically this is the visible range. So whenever we are interested in doing the temperature mapping, so we are looking for that okay, we are able to directly by human perception of eye, we should be able to see that image. So that comes under the visible range. But again, I would suggest that it is not the complete thing. Basically, apart from that also, by using the electromagnetic waves, we can have different type of imaging. We may have seen our X-ray from medical treatment perspective, and again that X-ray waves are not visible, but it is also going to give us the imaging, and that carries sufficient energy to penetrate into a significant volume or the material, and we see that how the X-ray looks like. This is one way. Similarly, the other extreme end, that is the long wavelength, that deals with the IR radiation basically. We may have heard about it. Basically, IR wavelength is nothing but infrared that depends upon the complete temperature sensation, depending upon the radiation emitted by the object, depending upon its local temperature, it's emit different kind of radiation. And if the sensor is sensitive to that thermal radiation, then it will just depict some image actually, and that is the basis of the IR thermography. Not only that, we may have seen our ultrasonic images also during the medical imaging inside the stomach or something like that. This consists of the sonic images. So high frequency are generally used to see the inside of the fetus or inside of the stomach or anything, something like that. So this gives the idea that okay, it is not only imaging is not only linked with the visible spectrum, but it is linked with the varieties of the wavelength spectrum, and depending upon the usage, depending upon the properties, or depending upon the nature of application, it is being exploited, and that happens. So now, coming back to our basic topic, we are going to deal it here, the visible wavelength imaging through the digital cameras. So once we have to, right now it became very miniaturized. Everyone has the camera, digital camera inside our even mobile also. But if we are going to deal the things from the analysis and technical evaluation estimation perspective, so the camera component, machine vision basically we can say, it consists of 2-3 different components. The first thing is that we may have heard that the camera, olden days the camera frame film was there. Instead of film, basically right now it has been replaced by either CMOS or the CCD. So generally we use the CCD based camera, that is the one component. Then next component of the machine vision is that most of the time during our laboratory analysis, we take the data and we wish to store the data, means that we wish to store the images for the appropriate analysis so that we can do the technical analysis. So it means we have to store it in the camera. From the camera, whatsoever signals are coming, it has to be stored inside the computer basically. And for that, there is another device that is typically known as frame grabber. So this is second major component of the camera, and it get connected, the camera get connected with the machine through the cable basically, and whatsoever image comes onto the through the screen, through the lenses, we can see that. The other component, as I talked about UT, that is the CCD. CCD is typically termed as charged coupled device. Depending upon the light intensity or emission, it get converted into the electrical signal, and that is finally going to be imprinted upon the through the CCD and transferred to the camera, to the computer, and that is being stored. So this is the part of the digital memory. The camera read the image in plane by plane, row by row. Basically, it is a matrix, just like a digital matrix. Say 5 into 5 pixels are there, means 25 pixels. So it means the field of view has been translated or converted into 25 zone, and each pixel represent the color or image information for that specific zone. So then how it is getting connected? Now we can see that this is the lens, and this became our frame grabber, okay, and that is going to getting displayed through our screen, and by using some machine vision algorithm, we can convert that information, visual image information, into a certain digits basically, and that we can use by doing the certain calibration. We can use that digit as the indication of the template. That is the whole idea. So now basically when we see that okay, the camera is capturing the image in the computer, basically again there the camera, what we see it, that can be defined in two ways. One is it is based upon the grayscale model, and the another one is that it is based upon the it is based upon the color model. So the grayscale model means we have seen our in olden days the pictures are generally black and white combination. Again, it is not like that ki, completely white or completely bright. Basically, it comes in different shades. Say 0 to 255 is the scaling factor. So depending upon the grayness factor, the shading basically that became the basis of the grayscale model. The other comes to be around the color model. What is the thing? What happens after these two models? First, I will deal it later. How the model works upon. Now, first we have to understand that through the digital imaging, what we are going to do, we are digitizing the image. Suppose this is the physical image of a man, and this is represented by this number of matrix. Say we can see the grids. So every independent square, a small square, represent a pixel. So this whole information of a man is imprinted upon the CCD, and that has been translated into the certain matrix mathematical form, where through the digit basically. So this is one of the thing. And then the other terms comes into the picture, the sampling, that measuring the value of an image at a finite number of points. At what points, and quantization. As I say, okay, we wish to quantify the grayscale. If it is say 0, completely black, or completely white, or in between different shades. So this is typically known as quantization basically. So image digitization, we can understand it in this manner, that image sampling, we can say, to understand the sampling, this is the complete digitalization, and this is the sampling space between two of the different pixels. So this is known as how we are going to sample it. And the image quantization, as I said, suppose we say white is 0 and perfect black is 255, and it has been divided into 255 shades basically. So then each shade will indicate on the basis of, it will be represented by appropriate digits, say 100, 200, something like that. And depending upon that, the computer is going to generate the color. So this is the grayscale model. To understand the sampling, I will show this image. This is the original image. How a picture of a girl look like. What will happen if we are sampled by 2 factor? Now we can say it is means 2 samples to a space has been factored by, and now we can say that it is slightly much more hazy. If we will increase sample by 4 factor, now means ki 4 grids basically we are representing by a single unit, so this becomes slightly much more blurred. Similarly, if we sample it by 8 factor, it will look something like that. The original image was basically, this is the complete analogous image. So depending upon the sampling factor, it will be appearing on the digital camera. This is sampled by 8 factor. Now quantization, basically what does it mean by? It says that, as I said, the real 0 becomes completely white, perfect jet black became something black, and in between how many shades are being created. So the bi-level or 1 bit per pixels. So means colors are black and white. Means if 1 bit per pixel is bi-level, means either in black and white image, if either it is white or it is black. So we can say that that is known as a perfect black and white image. But if we will pixel value by to the power 4, 8 or something like that, so it will produce 4, 16 or 256 shades of grayscale. It will be much more smoother and much more realistic representation, because in real life nothing happens in 0, 1. It is not like that. The object can be neither perfect white nor can be perfect black. It should be in between. So now just to see that 2 gray levels means 1 bit per pixel. If the information is stored in a manner that it is going to, for each pixel 1 bit has been taken into picture, means the tool, this is the perfect example, either white or either black. If we will increase it by 4 gray levels, means 2 bit per pixel, 2 to the power 4, so slightly we can see that the image became much more smoother. Now it is discretized, or it is appearing in 4 different shades of blackness basically. Now again, if it is information is stored 3 bit per pixels, then it became 8 gray levels, 2 to the power 3 basically. Means 8 shades of the gray scale has been there, and that has been categorized here. Now the next is 4 bit per pixels, that is 16 gray levels. So this is again much more realistic. We can see that the picture looks not discretized, it is a smoother version. If we will further increase 32 gray, 5 bit, 6, 8 bit, this is the most realistic one. So most of the grayscale camera, or we can still black and white images, works between 8 bit per pixel, meaning 8 bit information per pixels has been stored through the camera, through the frame grabber on the computer hard disk. So that can give us a 256 gray levels basically. So it will be much more realistic. Now that was the quantization of the black and white images. Now the other model for the color is, it is the color images. So color is generally, we know from our school days, it is the combination of 3 different component of the colors, that is the red, green and blue. By mixing these red, green, blue in different shades, different proportion, we can get the complete, with your complete 256 range of the colors basically. So it means that the total bit, there it was only one information, black and white, 2 bit, 4 bit, 8 bits, 16 bits, something like that. Here basically there are 3 components, means red is one thing, one shade, just like grayscale, green is one shade, and blue is one shade. So the color depth is often used 3. Here what will happen, the 8 bit image means 3 bit for red and 3 bit for green, and we can allocate 2 bits. It means in the 8 bit per pixel, by using the grayscale, it was completely going to get at the complete shades for the grayscale. Here complete shades will be, for the blue it will be 2, for a green, red and green it will be 3 3, and for blue it is going to be the 2. So with this we can create the complete spectrum. The quantization, we can see that this is the actual image, left one is the 24 bits, and we can say right one is 8 bit. So 24 bits is much more realistic. It will carry lot of memory space. We know that by right now, presently, basically in the present era, the memory size is not an issue, and therefore people can go with very high megapixel images. So it means the color quantization can be of extremely good in nature. So generally 8 bit is used into the color, and the 2 colors are basically have a color depth of 24 or 32 bits, any 8 threes and 8 fours, something like that. The 32 bits became too much memory based, and that is an excellent representation, but obviously that requires huge amount of memory to store. It can be 16 or 24 image per megapixel per image, and obviously in our real life, if we are going to store say hundreds and thousands of images, so it will completely fill the hard disk. So that's why we do certain kind of optimization while selecting that what should be the color depth. And how the computer see the color, computer see the colors in a matrix form, means at each location it is going to give the function of red, green, blue, means it will give, we can get the value of red, we can get the value of green, we can get the value of blue basically. And the other aspect we should be aware about the digital imaging is that the generally 5 formats that are we use it to save these images. These are the GIF images, PNG images, JPG file, TIFF file, PGM, or flexible image transport system. So these are the common prevalent format of the file in which we generally store the information of an image. So that's why we can say that these are the extension of the file name. And as far as the image formats are concerned, we can see that PGM stores say number of bits, we can see that JPG, it is the most loosely represented representation of the color basically, and TIFF, that carry better resolution, better memory, basically more space, more information. Similarly, something of that sort. Depending upon the nature of application, we can store, and depending upon the memory limitations, we can store the image basically. So now we understood that okay, grayscale means at each pixels we are going to have only one shade, between that will vary between 0 to 255. Now once we are dealing the color images, means each pixel should have three values per pixel. Means it should have the quantization, what is the value of redness, what is the value of greenness, what is the value of blueness. So with the proper mixer, suppose we say 1, 2, 3, means red is in the proportion of 1, green is in the proportion of 2, and 3 means blue is in the proportion of 3. So if we will mix these combination, automatically it is going to give us a specific color, and that will be very specific. So in that manner, that we can say that this is the picture of a flower. If we will see that, to each, at say this is 4 pixels. So we can see that in pixel 1, 206, 126, and 9 means one is for redness, one is for green, one is for blue. Means for each pixels, 3 set of information will be stored. So that is going to be the basis of the color imaging. Now, as I said, the color in the real life, the color is when it constructed from 3 intensity map, means red, green, blue, and each pixel have a 3 vectors. Pixel have a color image 3 element vector, and that is going to give us the value of color basically. Again, what I will say, that this as the basis of a machine vision, means the machine see any color not in terms of a final color, but rather it perceive the color on the basis of 3 different values, 3 independent set of values. That is the RGB, means redness, greenness, and blueness. But in reality, a human eye perceive the color in a entirely on the basis of a different color model. When we see, suppose we see the wall, what we will see, suppose wall is greenish, but we are not able to distinguish that how much is the redness, how much is the blue, how much is the green. Similarly, skin color, again it is the composition of red, green, blue. So our eye, human eye, is not designed on the basis of a specific color model, that is the RGB color. We don't see the color on the basis of independent color component. Then how we perceive? We, our human eye, see the color in a entirely different color model, that is typically known as hue, saturation, and intensity. Basically here the hue is the complete, it is the function of all the 3 colors, means it is the function of red, green, blue. And intensity defines, suppose when you see a wall, basically you can see that when we are inside a room, wall is appearing, say any skin color. What will happen if we will flood it with the light? What will happen? It will be much more brilliant, and finally it might be possible the same wall of the same color, green or blue, that will appear as a white. Similarly, if we will switch off the light, what will happen? The same wall initially which was fluorescent and appearing as a green to us, that will appear as a black. So that is the deciding, what is the deciding factor? Means the color is same, the color, the unique property of that wall remains same, but it depends upon the intensity and the saturation. Means you can understand this in that way. Okay, when we take a specific color, we start mixing white into it. What will happen? It will be much more lighter. We take the green, say red, it will be light, it will be pink, and finally it can be whitish or pinkish white. Similarly, if we will start adding black into it, saturation, then it will be much more pink will be red, deep red, blackish red, finally it will be black, something of that sort. So that this is much more realistic color model on which our eye perceive the colors. So now basically we can segregate कि there exists, again as I have said, कि color model basically it is just to define a specific color. There are something, the color is a unique in its inherently, and to understand that color we can understand through the set coordinate system, means RGB or HSI. Similarly, there is another color model YMCK that is generally used in our printing purposes and all that. So the color model as is an orderly system for creating the whole range of color from the set of parameters. So this cubes gives us the idea that how red, green, blue, different composition that is going to be created. Now RGB, as I said, it is not natural color model. Our eye perceive the color on the basis of a different color model, that is the HSI. So we will see that how we can correlate both of these things. This is a typical RGB color model, and to understand RGB color model, you try to see, we may have heard about the filters. This is a original image. This is a original image. And what will happen? This is a red band. Means it is allowing only red to pass on and filtering all the other colors. So the same image with red only, it will appear something like that. Similarly, this is passing through the green band. The same color will look with the green band something of that sort. And similarly, this is the blue. If we will properly mix it, amalgamate it together, then that is going to give us the final original image. Okay. Up now with the same original image, if we will extract a red, basically what we are doing it, we are extracting red and green and blue components are there. So it will appear something no red. Similarly, if we will add no green, the only green is filtered and other color are allowed, means red and blue, then it will appear something of that sort. And no blue, it will appear something like that. So a real RGB color based model is going to give us a complete color perception. And another model, as I said, that is CMY model. It is used in our printing industry. That is much more better for that. So depending upon the application, basically, now at this stage, what I will say, we will segregate. We understood a grayscale color model. Rather, lastly, we understood what is the black and white color model and the color model. So the color model are generally RGB type or the HSI type or CMY color. This is the thing. And HSI, if you will ask how it perceive, as I said, the triangle, this three corners, red, green, blue, and if we will mix it, it became RGB, and in the vertical direction it will be whiteness, and in the bottom direction it will be the blackness. So this is going to be the HSI color. Okay, I hope my voice is clear.
Yes, sir.
Are you able to hear me?
Yes, sir.
Yes, everything is okay. Fine. Continue, sir.
Okay. Okay. हाँ, मेरी वॉइस आ रही है? ठीक. Now we see that average human eye at a single go, it cannot distinguish more than 255 colors. It can more than 200. It can right now, suppose we are seeing it, we can understand the different shades up to the order of 200 hue basically. And saturation, as I said, pink has the same hue value as red but less saturation. Means if we will increase, suppose there is a hue, as I said, what is hue? Basically, hue is the combined function of RGB. It means it is the correct representation of a color. digital representation. And depending upon the intensity and saturation, it can appear as a black or a red. So this is hue wavelength, dominant wavelength, this is saturation, and this is intensity. So if intensity is 100%, it will be say white, and it is something of that sort. So HSI color model works in this manner. Now, basically, as I have shown that color HSI color model, we can see that the hue is basically defined in terms of angular displacement. It is varying, say, either it is defined on the scale of 0 to 180, or just like on gray scale, we can define segregate in 256 different color, and a different value of hue. It can be scaled on 0 to 255, or generally we define it 0 to 180. Means 0 to 0 degree is typically red, up to 120 on that model we will go, then it became green, and 240 degree it became blue basically. And saturation values again varies between 0 to 1, and intensity varies between 1 means 100% black, and 0 means no blackness is there. So on that way, basically we can mathematically, if you will ask with me how H is related with GB, again this is one of the formula. Again, it is, don't think like that it is a unique function. Variety of different color models based upon hue, different camera system use slightly different functionality. This is a typical. And saturation is defined as basically distance between OI divided by OS, and H is nothing but the tan inverse of the this complete, and I is nothing but the R plus G plus B divided by whatsoever is the value of R. Say the value of R is 60, 70 of for G, and 80 for blue, then the intensity will be divided by T basically. Though, as I said, it is not a unique. Some people have given other mathematical formulation for the hue, HSI, and each, same in MATLAB. Suppose we are using the MATLAB to disintegrate any image into the HSI, then it will use certain these kind of function, and depending they do not deviate much, but the only idea is that they might be claiming that this is the better representation of the color. Now at this stage we can get puzzled okay, what is the, we understood these kind of color models are there, so what we have to choose for what kind of purpose. So for display printing, generally RGB or CMY for printing. For displaying, RGB is sufficient enough. And for analytical analysis of the color difference, HSI is the most suitable one. For storing, we can use, again there is another YIQ, YUV, YBCR, CBR, something, these varieties of color models are there. So right now we are concentrating only HSI color model. Now we understood the fundamentals of the imaging. Imaging means how space wise, how does it looks like that, what is the meaning of the sampling, what is the meaning of the bit per pixel, what is the pixel size, what is the spatial resolution, and how the color information is being stored in terms of different sample size on the computers. So means 32-bit or 16-bit, something of that sort. Now once we understood okay, any image will be of that type, the second part of today's lecture is the liquid crystal thermography. So the liquid crystal thermography, that is a now basically the question is that what is liquid crystal. So I will suggest the best example is that the liquid crystal screen of our TV or computer. You can see that that can display the complete range of color. So these are typical inside it. These are the typical liquid crystals. So why it is known as liquid crystals? Basically, it is we know that generally we understand the substance in two distinct phases, or we can say three, basically liquid, solid, and gaseous phases. So in the gaseous phase, the molecules are completely free to move. interdistance between the molecular arrangement is not a restriction. But in liquid phase, they are loosely bounded. The distance are fixed, but it is not. It can move in. Liquidity exists, and solid it is permanently fixed. So liquid crystal gives it is a organic compound that is sometimes behaves as a it has the unique feature of reflection just like the solids, and it can change the structure also. It behaves as a liquid. That's why it is known as liquid crystals. So flow like it a liquid we can say, but maintain same order of structure just as a crystal. So this is a typical image of a liquid crystal. The chemistry people, they understand the things in much better way. So the liquid crystals are generally used for varieties of application, not only for the thermography. As I have said that on the computer screen, again there is also the liquid crystal. Our mobile also, old days LCD screen display, they are the liquid crystals. But again, liquid crystals can be sensitive to varieties of the stimulating factors. The stimulating factor can be the electrical signal, it can be the shear stress, or we can say the pressure, or it can be sensitive to the temperature. So if it is typically these are the liquid crystals images, basically chemical level by molecularly, how does it look like that. So it comes in different phase. The first is the symmetric phase, close to the solid phase of this. It is really orderly, we can align. Okay, they are restricted in their plane, and more order and higher viscosity. Another phase of liquid crystal is close to the liquid phase, means molecular in this phase are long and rod like shape, but they are free to move in the space. Okay, they are arranged in a random position, but they are restricted, they will move together. This is the nematic phase. And third phase is the chiral nematic. This is the twisted structure. So this kind of liquid crystal is found that they are very much sensitive with the colors. Depending upon the exposure of the temperature, these chiral nematic liquid crystals just change their pattern. The moment it will change the pattern, what will happen? The light falling upon it, it will display a different color basically. So it is a temperature sensitive paints, we can say that. The idea here, the principle here is that this is our liquid crystal, and we are seeing it depending upon the light intensity. Light intensity is coming, and this is the phase of this. And depending upon the temperature, it will organize in a particular order of the crystal pattern, and that will become the representation of the color. If the colors are, liquid crystals are organized in a specific pattern at particular temperature, so it will display a unique color basically. The moment the temperature will get changed, again the liquid crystal the structure will get changed. It is very found to be very sensitive to the heat. So this typical liquid crystal sheets became the basis for, or the liquid crystal we can say, became the basis for the temperature mapping. So this is a typical image of a liquid crystal that displays a beautiful pattern of say millions of colors onto it. So it exhibits a specific color depending upon the specific temperature. So this is the typical image polarized under the liquid crystal visualized under the polarized. Now the next question is that, okay, we understood that these are the organic compound in which the molecular arrangements behaves sometimes as a liquid, sometimes behave as a solid, and it has a unique property of liquid also, solid also, and it displayed the range, it just get organized, and it display a specific color range at a specific temperature. That is the liquid crystal. Now, how to use it? It comes in capsulated form and it comes in uncapsulated form. Means capsulated, we may have seen the capsules. Our drug or the medicine are inside it and it is coated within the capsules. Why? To safeguard the drug from the contamination, from the oxidation, some external environmental factor. So similarly, liquid crystal particles can be encapsulated within a complete some kind of coating of the order of 5 to 10 micron, or it can be encapsulated. It comes in the form of powder, solution, or prefabricated polyester sheet. Means these liquid crystal powders can be there. It can comes just like a suspension solution also, or in a sheet. That is very user friendly. I think Professor Adnan has used the prefabricated sheet. That is, and it liquid crystals are available to measure the temperature from say 30 minus 30 to 120 degrees centigrade. So liquid crystals again can be further segregated, categorized in narrow bandwidth liquid crystal or the broad bandwidth liquid crystals. So next question is that the people, those researchers who are going to dive deep into it, they are going to start the research based upon liquid crystal thermography. First, we have to understand how it has been designated. So a typical temperature sensitive liquid crystals, we can see the right hand side say R25C5W. R stand for means in the native state, if the liquid crystal polyester sheet we will take it, it will appear completely black. It will not show any color. The moment it is exposed to a crosses a threshold of a specific color, it will start appearing as a red. So means suppose it is written R25, it signifies that the red start at 25 degrees centigrade. And C stand for unit, means if we are designating in terms of Fahrenheit or in terms of centigrade. And 5W means it is the bandwidth, means it will start appearing, the color red will start appearing at say 25, and the moment it will become 5 degrees, say 30, it will again go back to the completely black. So within that bandwidth only it will display the complete set of information or the colors we can say. Similarly, another class of liquid crystals, they are typically sensitive for the shear stress. They are typically designated NSL 40 or something of that sort. So this is entirely. Right now our focus is the kind of liquid crystals that are sensitive to the temperature for mapping the temperature pattern. Now, what are the strengths? So we are comfortable with dealing the temperature with the help of thermocouple. But the difficulty with the thermocouple is that it is a point measuring technique basically. Where we will mount the thermocouple, there only it is going to give us the color. But in reality, what happens in the machine components, some local hot spots are there, some cold spots are there, overheating will, overshoot of temperature will be there, it will change it, it will harm the machine. So that's why if we are understanding or designing it or analyzing any machine, then we have to be very sensitive that the temperature should be correctly patterned, understood. For that, thermocouple is not the suitable. So in that way, liquid crystal, as I said, the size of each liquid crystal particle of the order of 5 to 10 microns, means each liquid crystal particle is able to display the complete 256 range of colors. Means it is acting as a thermocouple. Means up to the spatial resolution is extremely high. Means how much high? It is of in few microns. So that is one strength. The other thing is that the response time is very fast. It is lag is very, because the thermal mass is very less. That's why it is these two things resolution wise, the resolution is of the order of micron, but again it is not restricted by the liquid crystal size, rather it is restricted by the imaging of the digital imaging resolution basically. Means if the image stores the color in 5 megapixel, 2 megapixel, something of that sort, so depending upon that resolution, it is going to give you the idea, as the idea how much is the spatial resolution. If say 1 inch is displayed by 1 square inch is displayed by 100 pixels, 10 into 10, so it means ki every 1 pixel will represent 1 by 10th of the inch. If it is the same 1 inch is captured by using say 10 megapixel camera, then it might be a different, completely different story. So that's why that is the strength. And this is a typical liquid crystal image mapping the temperature of a electronics chips basically. Now we can see that it shows a different changing color. R is the most coolest region and blue is the most heated region. It can give us the complete temperature pattern. That is the beautiful image. And again, this is a typical combustion chamber in which the combustion is taking place. The swirling flow, we can see that here how it is being captured. I mean, depending, it is swirling it, and how the temperature is getting changed, it is completely captured. So this is the strength and beautiful world of the liquid crystal. Okay, when it gives the complete quantitative information, and this color can need to be correlated with the temperature. So right now, until now, we are just concerned with we covered the aspect of the machine vision and the color. Now the next stage is that this color has to be mapped just like in thermocouples. What is the basic quantity? Depending upon the temperature, a thermocouple sense the temperature and give us the electrical signals in terms of millivolt. And if we map temperature with the millivolt, that became a calibration curve, and that became, by using that calibration curve, depending upon the millivolt, anyone can estimate the temperature at that point. So here basically the color need to be converted into the temperature. So for that, to perceive any color, the first criteria is that, as I said, the example that, okay, suppose we want to, wherever we are sitting in our room, varieties of the colors are there. So we are seeing all things together. But there should be the light inside the room. If there is no light, we cannot see any color. So from that angle, when we are looking for machine vision, so we have to define that what should be the threshold range. If between that intensity level, whatsoever the camera is capturing the color, that is the true representation. So it has been documented by the research that if the intensity is of the range of, on the scale of 255, if the intensity varies between 80 to 100 or 110, 20 I can say from my experience, then that will reflect the true color representation. Okay, so that is, so suppose whenever we have to calibrate, we have to fix the lighting condition. We should not alter the lighting condition. If we are doing the experiment, our lighting condition should be frozen, and depending upon the calibration curve, basically later under the same illumination level, we have to map the temperature. And now another aspect is that I have shown you the image of the camera that was written as 3 CCD. So what is the difference? 1 CCD, generally most of the camera are 1 CCD. There is 1 CCD only. Means on a single CCD, all the 3 components of the color is falling in terms of light, and it is sensitizing, stimulating, and it is being stored in terms of RGB. But there is a special class of camera that is typically known as 3 CCD. How does it behave? It is, each CCD is designated for a specific color component. Say for red 1 CCD, for green 1 CCD, for blue 1 CCD. Means it is something like that. We are storing the information at the level of directly storing the information. We are storing the each component entirely different. It is not like that through the software arrangement, we are not splitting a single color, single digit into 3 component RGB. Rather, we are taking RGB independently. It is something like that. To understand it, we can say that, okay, if there are 3 layer of rivers, one is giving complete red color, another river is coming, it is green, another is blue. So we have better autonomy. We can understand the real color in a real manner. So 1 CCD versus 3 CCD. 3 CCD is hardware level page is much more better. We are not doing any processing. Now for calibration, what we have to do? So suppose we have to map the temperature over a surface. So what we have to do? We have to clean the surface first. TLC stands for thermochromic liquid crystal. Means the liquid crystal class which is depending upon the sensitive to the temperature. subject the treatment surface to the, and first it has to be exposed to a known temperature. That is number one. And then record the color response. And what is the requirement? As I said, the requirement is, first requirement is the uniform lighting source. And then that surface should be isothermal, so that we have whatsoever color is coming, a single color should be assigned with a single value. That is, this is just like the analogous calibration voltage to temperature of thermocouple. Again, next question is that what should be the kind of light? The light, again, it is not like that any light will work. The light, ideally speaking, technically we say the light should be white light source. White light means, it does not mean even the halogen is treated as a white light source. White light means it contains all the wavelength with your complete wavelength. So our sunlight is a perfect example of the white light source. And similarly, our tungsten, we will not use our tube light. That is a fluorescent, that is a flickering effect basically. So generally we have to use either the tungsten light or the LED light or any natural light which is appearing as the white. And again, for liquid crystal are generally found to be very sensitive to the ultraviolet or the infrared radiation. So that should be free from that, because IR itself carry the heat. So if we are heating the liquid crystal by a IR imaging, then it will alter the temperature. So it should not contain, the light should not contain free from the heat source as far as possible, or it should be free from the ultraviolet. Otherwise, it will harm the liquid crystal pattern, permanently damage it. Okay. If the light contains the heat, then we have to see that the duration of experiment need to be very less. It should not be too much, so that it should not harm the original signal of the temperature. This is a typical image of a liquid crystal sheet pasted over a heated plate. It will appear as a blue. Now, what we do, suppose we have selected a 50 by pixel and beneath it we have put a thermocouple. Means suppose we are taking, this is aluminum plate, so within that region, say 1 centimeter, temperature can be treated as a isothermal. Say whatsoever temperature is coming, we will take again any image. We know that any single data cannot be taken as a signal. It may be noise also. To ensure that it is the true representation of the actual signal, we go for the average. Means 50 into 50 pixels, we will average it first, so that we can say that is one representation, and that we will map it with the pixel. Now this image shows, this is a typical HSI representation of a temperature of a typical liquid crystal sheet whose bandwidth was between 35 to say 40 degrees. Now we can say that the hue, we can say red color, it is a very unique and monotonic variation with respect to temperature. Other things is also varying, but it is not that much very good. So this H is generally used, and it has the least variance also. Means it is not varying much within the selected size. So that's why this is typically, if we fit a curve within it, say third order, fourth order, fifth order, sixth order, and that curve will be used to get the color converted into color into the unknown temperature. That is just like the analogous of the temperature. So this is a typical liquid crystal sheet, heated plate, and it is showing a different range of color. Suppose the first, what we have to do, we have to first complete the calibration exercise. Once we get the calibration curve, we have a curve. Polynomial coefficients are well defined. And if we take the image of a unknown heated temperature plate, it will take something like that, and each pixel will have certain value of H. And that H, depending upon the calibration curve, will be mapped with a particular temperature. So the whole temperature surface pattern of color can be converted in terms of temperature. So basically, on concluding note, we can say that this is a very exciting field. The uniqueness, strength lies in spatial resolution is very high, response time is very good, ease in use, flexibility. The best aspect is that we have to suppose the map the temperature of a curved surface. Then what we have to do, we have to take the liquid crystal, paint and spray onto it. Again, it will, depending upon the shape, it will change it and it will give us the color. We can apply it on the flat plate, curvature. The only thing is that we have to judicially select, sometimes polyester sheet, sometimes spray, sometimes powders. We can mix it in the liquid. Again, the liquid, if it is homogeneously mixed, the each location within the liquid will act as a stimulating and it will display a color. So these are the things. It is very useful in the solar energy research, biomedical, gas turbine blade cooling, MEMS designing, chips, microchannels study, and all that. Application, if you will ask, it has enormous potential. I think it's something I will cover in the next talk on next week. So liquid crystal application, these are the real life images captured by using liquid crystal in the laboratory condition. This is the freezing of the water under cold surface. This is the convective flow seeded with liquid crystal. This is it illustrating a typical convective pattern. This is a water impingement jet on a heated plate. So this can be the varieties of application. Again, this is a heated water inside a beaker. Basically, some liquids are there in which liquid crystal powders has been mixed, solution has been mixed, and it can show the complete temperature pattern. It is a very beautiful tool for studying the convective patterns also. And again, medical imaging is also one of the field. We can see that depending upon, in the old days, people was doing the mud therapy, and here we can see that depending upon the suppose liquid crystal has been pasted upon, then it will display the color, and it is typically known as a to find out the allergy. Wherever there will be local hot spot, we can get it. Similarly, it is a very useful tool, non-destructive tool to map the suppose whenever there is a ulcer or the cancerous cell, at that location the temperature of the body will be very high. So just without any radiographic based imaging, it can give us the tentative idea that this is the heated zone. There exists some trouble within the body, and that we can look for. So this is the medical imaging. Again, the electronic chips, these are the these are all temperature patterns. And then in the, I will summarize that in solar heater to map the temperature pattern, heat exchanger, radiator passage, gas turbine blade cooling study, electronic, everywhere it has strong footprints and presence of liquid crystal. This is a typical, we can see this is a typical liquid crystal sheet without any surface. It is a flat surface. We can, flow is happening in this direction. We can see how the temperature is changing. If we have put a rib basically in between, we see that how it is changing the color. You can observe that here the left wise, it is no breakage of the boundary layer, no turbulence for motor, that's why it is remain heated. Here if we put some disturbance in between, these are the reattachment and all that, that is going to leave us a liquid crystal transient images. Similarly, the moment once we got the temperature pattern, the next stage is in our heat transfer study is that most of the time we are interested in convection study, we are interested in finding the heat transfer coefficient or say the Nusselt number. How to do that? For that, we can take the transient images of the, or say the temperature or the color of the surface with respect to time, that can be used for using the conduction modeling. Say T is the function of temperature, initial temperature is known, air temperature is known, then H is only unknown. We can satisfy this is a one dimensional semi-infinite conduction solution. On the basis of that, the temperature pattern images can be converted into the local Nusselt number. So it is going to be a very useful thing. And the same data what I have shown earlier, that has been finally converted into local Nusselt number. This is the process data. So this is another application. And some of the things what we are doing it here, we are implementing the boundary layer research, and these are the prevalent rib configurations on the surface, and there we can see that Generally, this is the type of flow happening here, and we can capture the temperature at the surface, correlate well with the flow structures, and then understand them. So this is one way. This is one of the excellent setup in our lab, which is we have used for the fundamental flow study, or you can say the gas turbine blade cooling. So this is one of the, these two are the halogen lamps. This is the crystal sheet. At the top, the camera is there. We capture the camera from the top, and then when the wind is flowing over the inside the stuff. These are the typical processed local heat transfer distribution over the ribs. We can say depending upon the configuration, the heat transfer rate will be different, and we get the different pattern, and that gives the complete idea, beautiful idea about how the local hot spots are there, where the temperature is more, where the temperature is less, which is the vulnerable zone. So that we can design intelligently, we can predict the failure. These are the set of images. These are the actual, it looks like numerical, but these are the actual images of the liquid crystal. This is again surface wise, we have used the PIV technique, and we have correlated the flow information very well with the temperature. And then we found that we are in a better position to explain the fundamental of the flow. So on that note, I will finish this today talk. I will ask that if from the audience side, if anyone has any question, kindly let us know.
Thank you, Professor Kandale, for a wonderful
Okay.
talk, for a wonderful and excellent talk. So now I'll ask the audience if they have some questions, if they have queries.
Can I get the interact with the audience?
You can interact. You can go ahead and interact with the audience. Audience.
Okay, I hope that this it was sound was
The
not
sound was okay.
okay.
So do we have a break now? No, we are just going non-stop. Actually, Professor Kandale, we had to take a break of 10 minutes. Chalo, theek hai, it doesn't matter. So they can just ask you questions.
Okay.
Just let's wait for some time.
Okay.
Hello. Hello.
Hello.
Hello.
I am hearing.
Hello.
Hello.
Hello, sir. Good evening, sir.
Good evening.
Myself, Gautam from NIT Srinagar.
Okay.
Currently, I am second year student pursuing BTech.
Okay.
Sir, I want to ask doubts regarding liquid crystal thermography. Is it economical? How much does the thermography
certainly, depending upon the quantum of information, I can say it is economical because, okay, suppose we are using a thermocouple. Thermocouple is very cheap in compared to liquid crystal thermography. Complete setup basically. It requires the camera, frame grabber, computer, image processing software, and all that. So from that angle, it is a costly thing. But if we will see that in a single shot of a surface, we are getting millions of the color, and that information from that perspective, if we will go for the thermocouple or anything, it will be not possible, and if it is possible also, then it will be not economical. So it is not very costly, and it is very suitable for the design of the machine. Not very costly. If someone is interested in, he can start, depending upon, he can take one camera, frame grabber, computer. I think it is these days, these are economically valuable.
Hello, good evening, sir.
Good evening.
So this is Dr. Gurpreet Kaur from Jammu.
Okay.
Sir, I just want to ask, you mean just by purchasing these simple instruments, one can start liquid crystal lab at one's place?
Sure, but as I said, you have to. It is not a unique instrument. Okay, you purchase this one and you can start. Basically, liquid crystal sheets are generally supplied by. There is only one supplier, that is Hallcrest, UK based.
Okay.
So the liquid crystal sheet comes, I can say 1 feet by 1 feet, 30 centimeter by 30 centimeter square sheets are there. Suppose there is a long surface, we have to paste, join it, something of that sort. So liquid crystal sheet is one of the major component. Then depending upon the money, you can go for the quality of the camera. We know that the camera comes in.
How much does it cost, sir?
The camera, again, the quality of the camera. That's why I am telling. A machine vision camera, it can be 4-5 lakh.
There is
Liquid crystal sheet will be.
Sir, actually there is.
Go ahead.
So actually, I mean to say, if one wants to start a lab for the students of undergraduate for doing some research of liquid crystal, so is it possible at the college level that we can start
How
with
much money is in
establishing a
your
lab?
mind? How much money is in your mind?
Around 30 to 40 lakh.
More than enough. More than enough. It can be 15-20.
That can be financed by the department. Actually, we are under NEP. We need to start some initial research at the
40 lakh is a
undergraduate
very
level.
good amount. Very good. I would say that we can get it within 10-15 lakh.
Okay, that's very good. Sir, I will contact you later on about establishing the lab.
If you have more money, you can go for the high-end kind of instrumentation. More bit rate, more sampling size, more megapixels, better quality of the computer to process the data. Lot of for enhancing the spatial resolution, temporal resolution, high frame rate, supply image. These things are there. But certainly 10-15 lakh can be a good start.
Okay, sir. I will definitely contact you about establishing the lab in our college. You
Sure.
please थोड़ा सा हमें guide करिएगा regarding this.
Sure, why not? Why not?
Thank you,
To
sir. Thank
connect
you
with
very
me,
much.
you can get my number, or you can get already my email is there.
I will get it from the convener of the FDP. Thank you, sir. Thank you very much.
So what about the errors in temperature measurement while performing LCT?
It is say 0.1 degree centigrade uncertainty of that order. Point 0.1 degree, and as I said, in say milliseconds, few milliseconds will be with the temporal resolution. Spatial resolution is again very high in microns, 10-15 microns, something of that sort. Recently we have implemented this. Again, I have not shown that slides intensely today. We have implemented liquid crystal sheet in TCC measurement. That will be the scope of my next. Okay, anyone else?
I have a question.
Sure.
Professor Gangli, how do you calculate the heat transfer coefficient
Heat transfer
from the information, from the images which you have captured from?
That's why I'm telling. Suppose we have the transient set of images. We capture say 10 images, 20 images for a duration of say 30 seconds or 10 seconds. So what we have to do basically, again, it is a kind of conduction modeling. So we know that semi-infinite conduction solution is there. If a surface is adiabatic, it does not, the heat does not get penetrated. So by using the one dimension, one boundary condition itself, we can get the solution. So as I said to you, I will show that equation basically. Can you see this equation?
Yeah. I can see the
Okay.
equation.
So
It's
this is the surface basically on which the liquid crystal sheet has been pasted. This is typically acrylic basically. So what will happen from the top if we are capturing through the camera? So
Yeah.
for a particular instant, say 10 seconds, if we captured it, so within 10 seconds whatsoever the temperature is changing, it is going to capture in 10 set of images. So say at instant 1, initially say the temperature was say 30 degree. So this became wall temperature became T initial 30 degree. And this is the air temperature, bulk mean temperature of the air. Say air was say 10 degree. So this is known, and this is with respect to time. So say
fine.
instant 1 some temperature, instant 2 some temperature, T1, T2, something like that. Now this alpha represent the diffusivity, T is the time, K is the thermal conductivity of this material. The material need to be the adiabatic basically. The heat diffusivity should be less, it should not get penetrated. Now we can see in this equation everything is known except unknown is H. H is the heat transfer coefficient. So if we will put the temperature with respect to at a particular instant, so at that instant it is going to give us the value of heat transfer coefficient. So again, heat transfer coefficient will be the function of temperature. So if we will take a long signal basically, so it is going to give us the average heat transfer coefficient over that time. I hope I have cleared that.
Yeah. I've understood it. So you tell me something about the calibration. How frequently do we do the calibration?
Calibration generally, if the lighting conditions are not getting changed and
Okay.
all the instruments and everything are fixed at that location, so I
Okay.
think we can use that calibration say even after 5 days, 10 days, there is no issue.
Okay.
Every day there is no need for calibration because physically it has to be a standstill at the same location. The camera, interrelative distance between the camera, the plate, and the lighting arrangement, everything is fixed. Then there is no point in doing the calibration again. The moment if we will slightly alter the location of the light, the lamp, or some room light conditions, or we have changed the location of the camera, we have changed the location of the light, we have changed the location of the object. In any cases, we have to then go for it recalibration under that. And once we do the calibration, we have to freeze all the set of instruments.
I say about something about image processing.
Hmm.
Nowadays, we are having in MATLAB, we are having an image processing library. We can process, I think, all these images and we
Exactly.
can
It
get
is
all
very
the
easy. Actually, just by a single command.
single command we can get
Single
all.
command. When you take that image, convert that into the HSI and write it. It
Numbers.
will write it. It can take the say. Suppose we are capturing a movie. Generally, for the transient measurement, we are capturing a movie. It is not a single image. Say 100 images. So it will take that AVI file, process it, split it in say 30 frame per second is there. Suppose we are capturing it. That's why I say depending special temporal resolution depends upon the camera speed also. Suppose we are each camera is taking 15 samples per second. Means 15 set of images per second. Means say 1 minute 15 into say 60. That number of it will split that frame in different frames, and each frame will be again discretized in terms of digit, in terms of hue value at each pixels, and saturation value at each pixels, intensity value means RGB values.
Thank you. Two more participants have raised this thing hands. I'll request all the participants when they ask the question, they should first of all introduce themselves. Amir, but you can just ask the question.
Good evening, sir. My name is Amir Subat. I am a research scholar at Heat Transfer Lab. I just want to know the difference between the IR imaging and this technique, and how is this technique better than IR imaging?
I think already I said the IR imaging is entirely a different class of thermography.
Mm-hmm. Mm-hmm.
This depends upon the substance is coated with the liquid crystal in the form of polyester sheet or in the form of paint, and that display, depending upon the temperature, it display a unique color. In IR, basically the object does not display any color, it display the thermal radiations,
Radiation, yes, exactly.
and that radiation is captured by a special class of sensor that is sensitive to the infrared, that temperature,
Yes.
and that is going to give us the temperature pattern.
Profile, yes,
It
exactly.
is nothing to do with the true color. Here it is, what we are seeing is that is the true color of the object. Say the liquid crystal sheet. Means the color we can see it when we are seeing the liquid crystal color, you can say that we are seeing the temperature. But in IR, suppose I am capturing your image, you are not showing any color. But your image will be captured by IR camera, it will display in terms of temperature.
So yes.
Okay.
So I want to ask, at the end we are measuring temperature, and IR technique is also a non-intrusive technique.
Again, the limitation with liquid crystal is that we cannot work with very high temperature.
Yes.
Not more than 100. Generally, people are using it well within 100. Again, as the thing is that you can ask the question, okay, people are doing the gas turbine research that works as 1000 degrees centigrade and 1500. Why it is so? Because we do all the experiment at low temperature, say 100 degree, 50 degree, 70 degree, something like that.
Yes.
The thing is that there we work with the non-dimensionalized quantity. Whatsoever is the outcome, we say that will be valid at high temperature also. Especially if we are neglecting the radiation. IR is very much suitable with high temperature. It can be we can measure the temperature. It is nothing to camera sensitivity is required. It is nothing to do that object can withstand that temperature or not. It can set the temperature of the order of say 1000 degrees centigrade to 2000 centigrade. But the limitation with the IR is that the IR camera are extremely costly.
Yes.
Okay. Here the camera will be of the order of 5 lakh, 6 lakh.
Yes.
Okay?
Yes.
And there the camera cost will be of the
25, 30.
is that the IR camera resolution is very poor.
Yeah, that is the one.
Of the VGA type. Suppose you are going with 1 megapixel, that is treated as a extremely high quality IR camera. That can be 70 lakh, 60 lakh, something of that sort. Here, we can get say 4 megapixel camera within 4-5 lakh. Or again, forget about the dedicated camera. I can suggest that you can use your photographic camera. That can be 25,000 or 50,000. That camera also can be used for liquid crystal.
Okay.
Because the only thing is that it should give you the image in the form of text or the
yes.
So even with a 50,000 camera, 25,000 camera, you can sense the temperature. Okay. There it is not viable. Here the resolution of the image can be very high.
Yes.
That's why spatial resolution can be very good. There the spatial resolution is. Again, the other thing is that there the temporal resolution cannot be very high. The frame rate of the general camera can be very high. It can be 30, 40, 60 something. In IR case, the temperature sampling size can be very less.
Yeah.
Okay. These are the things. Okay.
Mr. Gawak Shafi, I think you also want to ask. Mr. Shafi? Mr. Singh, you have also raised your hand.
Yes, good evening, sir.
Good evening.
My name is Rajbir Singh. I am a mechanical undergraduate at NIT Srinagar. Sir, I had a question that in CCD, what should be the minimum frame rate of the camera?
It is nothing to do. If a single frame also, in that frame it will sense the color. It depends upon that. Do you really require the transient set of temperature variation? Then you need the frame rate.
Okay, sir.
Suppose we are in some of the cases, people are doing the steady state measurement. So under the steady state condition, they are interested in getting a single image. That single image can be corresponding to the Nusselt number. है ना? So
Yes,
that's why that is also. I think Professor Adnan, you may have used the steady state or transient.
Transient. It was a transient one. Mr. Koshan, I think you want to also ask something.
Good evening, sir. I am Koshan Kari from Mechanical Department in IT Srinagar. I'm currently doing my bachelor's here. I wanted to ask, our lab might or might not have proper equipment for this experimentation. So, sir, can we use your lab instead?
No, see, these things are dedicated for the research kind of thing. When if some research problem are there, then certainly, as I said, it is not a single instrument. We have to prepare the test rig surface, and then we design everything, and then we put all the lighting, camera, everything into picture. It is not like a routine thing. You just put a thermometer and get that. And if you have any specific thing, you can come here. You can see that. You can see that.
Okay, sir. Thank you, sir.
Mr. Koshan, you have to plan the experiment. No?
Yes, sir,
You have to just plan what are the things which you have, because you have to develop a test cell, then plan things. Then you can use facility of Professor Andali.
Yes, sir. Yes, sir. Got it, sir.
Anyone else?
Yes, sir. I wanted to ask a question.
Please introduce yourself.
Good evening, sir. This is Gawar Shafi Bhatt from Energy Research Laboratory at NIT Srinagar. Sir, I had a question to ask.
Sure, most of
Sir, the question is that what is the feasibility of using liquid crystal thermography in rotating equipment? For example, in case of rotating blades.
See,
secondly,
okay, for second question.
So the second question is that what is the effect on the measurement due to the contamination? For example, there is water splashing over these liquid thermal crystals. How will the measurement be affected?
Okay, good questions. Actually, see, first we have to understand that liquid crystal thermography is nothing to relate with the motion. The only thing is that the camera and the object,
okay,
there should not be any interrelative motion between that one, because it has to be under fixed condition. It has been fixed, calibrated under that condition. If say there are two trains and moving at the same speed, then there is no relative motion. So when we are seeing the color, it will reflect the color. Again, suppose in a rotating blade experiment, at that instant, whatsoever image you will get it, that is going to give you the temperature pattern.
All right.
Suppose the blade is moving, say at the rate of say I can suggest say 10 rotation per minute.
Okay.
Or say 200 rotation per minute. Now, if you are capturing with the frame rate of say 50 frame per second, so it might be very high in compared to that rotation.
Okay, all right.
You got my point. So at that instance, when the camera is capturing, at that instance you will get the temperature. Number one. Number two question was that, if I understood correctly, in between some splash of the water or something.
Water, any kind of
Again,
contamination.
the thing is that it is nothing to relate with the contamination. It should be visually clear to the camera.
Okay, all right.
If the water comes in, the calibration gets disturbed.
Okay.
It depends upon the visibility, illumination level, and everything has to be same.
Okay.
If it is changed, it will not. But quantitative measurement wise, it might be okay.
All right, sir. Understood, sir. Thank you. Thanks a lot.
Anyone else? Anyone else wants said? Okay, I think this is all. So we all, on behalf of NIT Srinagar organizing team, I thank Professor Andali for an excellent and wonderful talk. So we are looking forward in hearing from Andali again in the next week.
Sure.
ठीक है ना? Okay. Good night. Bye. From NIT Srinagar. God bless all.
Thanks.
Thank you, sir.
Thank you, everybody.